So good morning, everyone. So as Indra said, my name is Alex Kono, and today I will present this project that I have worked for about 2 years with Jeff. So just a brief introduction. So transport is an area of high expenditure. So it's about 30% of the cost of sugar. And to minimize transport costs, mill staff called traffic officers develop locomotive run schedules. And to develop better schedules, traffic officers require information on locomotive trip times. So to talk how we designed this project, I need to mention 3 systems. So the first one is Steel Tools, which tells us what locomotives are supposed to do. The second one is the GPS system, which tells us where locomotives are at any given point in time. And also ACTS, which tells us the physical location of sidings and mills and railway tracks. So we then combine all these 3 systems to improve traffic operations. So the first system is called Steel Tools, and it's a computer-based tool to create daily schedules and to manage traffic operations. So this is a screenshot of a schedule for the 31st October 2013. So as you can see on the right-hand side, we've got 2 lists of locomotives, our locomotive runs. So it tells me what time they start and also what sidings were serviced and how many beans were delivered and how many beans were collected. So the majority of the locomotives, I think maybe all of the locomotives these days, they have GPS equipment installed. And at this stage, they are just used to add in trace separation at real time. And then once they are used, they are stored. So at the end of each crush season, mills end up with a whole stack of historical locomotive GPS data. But at the moment, they are not full analyzed. So this is an example of what the GPS data looks like. So we've got the locomotive here, we've got the date and time, the position, speed, and angle. So within Steel Tools, we've got an application called ACTS, which is a scheduling tool. And one of the features of this system is an interface with a GIS system called Mapinfo. So on the right-hand side, we can see a screenshot of ACTS running Mapinfo. So this system shows us the physical location of mills. So this is race course, the railway tracks running along, and also the location of sidings. So we then combine these 3 systems and develop our project. And our project consists of 2 algorithms. So the first one identifies run information based on historical GPS and Steel Tools data. And the second one predicts locomotive arrival time based on real-time GPS and Steel Tools data. But before we implemented these algorithms, we had to make some changes in ACTS. So the first one was to change the way sidings were represented. So before, as you can see on the left-hand side, sidings could only be defined as points. So when replaying GPS data, I would sometimes see the locomotive coming closer and then shunting somewhere far from the siding and then moving away. So it was hard to detect shunting activities. So we changed that. So now we allow sidings to be represented as polylines. So we allow the true representation of sidings now. So as a result, now we could see the loco coming, shunting the siding, and then moving away. So we also added in Mapinfo the mill yard area concept or mill yard boundary concept. And the reason is because runs usually start and finish at mills. So to detect the start or end of run events, we simply needed to detect if the locomotive exited the boundary. So like, for example, exiting or then entering the boundary. So this helps us to detect these activities. So once we made the changes in ACTS, we then started implementing our first algorithm. And the rationale behind is that better scheduling requires accurate information on locomotive trip times. So locomotive trip time information includes start and finish run events, shunt times, how long locomotives spend at junctions, at catch points, and delays in the system. So a junction activity would occur when local crew have to change points, or when they have to wait for other locals to pass, or when a locomotive has to service 2 or more branches. So in this case, the locomotive would stop at a junction temporarily and leave beans to pick up later. So we also have catch points, which is a crossing where the local crew have to set and reset the points when crossing it. And as an example, there is a catch point, Macaixuga, with the QR railway. And finally, we also want to detect delays, which by definition is the time when the locomotive is stationary during the run doing nothing. And that could be caused by crew breaks or just locals waiting for others to pass. So our algorithm that processes historical GPS and ToolTools data performs 2 steps mainly. So the first one, it matches runs based on run start time and mill. And then for each matched run, it breaks down trip times into well-defined events. So at the bottom, we can see a screenshot of ToolTools running our algorithm. So we ran this algorithm with Macaixuga data for the 2013 season, and we were able to match runs between the GPS and ToolTools data, and we got about 50% of the runs. So I'm going to talk about this figure later on. So once we finish tracking the information, we also added 15 reports to ToolTools to display the results. So they are divided in 3 groups: error reports, analysis reports, and speed reports. So the error reports show us problems when matching runs between ToolTools and the GPS data. Analysis reports show us, it summarizes run activities, and speed reports show us information about speed. So in the next few slides, I will show some of those reports. And the first one is called Travel Details Report, which is also the most popular one. So this report shows me at the top the details of this run. So it was a local name. This is the local name or abbreviation, the date, driver and assistant, if the crew was defined in ToolTools, and the run type. On the left-hand side, we've got a box which shows us the information provided by ToolTools. And then on the right-hand side, we've got a box which shows information from the GPS data. So we have a field called yard time, and we define yard time as the difference between the actual start time in ToolTools and the actual time the local left the mill yard. So in other words, the run was commenced at 1:42 a.m. and 3 minutes later the run started. And at the bottom of this report, we have a list of run activities that is loco performed in chronological order. So we can see that the loco left Marion Mill at 1:46, and then it traveled for about 60 minutes and arrived at Zarbiyard siding, and then it shunted for another 50 minutes. After that, it traveled again, and then it shunted at Marani 3 siding and delivered 60 beans in 10 minutes. So you notice that we have the number of beans assigned in this shunt, but not in this one. And the reason is because till tools indicates that this siding was serviced, but not the other one. So the bottom of the report, so we can see that we've got some other run activities performed by this run. So as we go on, we've got a shunt activity, a junction activity, and also a delay close to the end. And then at about 3:18, the run went back to the mill. And then at the bottom of this report, we've got a summary of these run activities. So the next report is called Yard Departure Report. So it shows us the average yard time for each driver within a certain period. So in other words, it tells us how long drivers spent in the yard once the runs were commenced in TL2s. The next report is called Shunting Details Report, and it shows shunt information within a certain period, either by loco, driver, or siding. And the data in this report is shown in box plots. And box plot is a efficient way to show data distribution. So just as an example, Perry 2 siding. So the box plot tells me that the bottom line was the fastest shunt in this siding. The top line, the longest shunt. The box itself holds 50% of the data. And then we've got this line with the median and then the mean value. So when I see a box plot like this, I would think that it's easy to predict how long shunt times are for this siding. But then when I see a box plot like this, I would think that it's hard to predict how long locomotives will shunt in this siding. So how long locomotives will take to shunt, because the box plot is quite large. So the next report is called Travel Audit Report. So it shows me run activities that exceeded a certain time limit. So for example, we've got in this report, it shows me shunts that took over 25 minutes. So I can see this report for shunts, yard, or delay times. So this is a report from the Speed Reports group, and it's called Segment Summary Report. So it shows me average speed based on color grades. So it's just an efficient way to identify bottlenecks. The next one is called speed audit report. So it just shows me locomotives that exceeded the speed limit during the run. And then after we finished this algorithm, we then analyzed some of the results. And to do that, we got Makai-Sugar 2013 data. And Makai-Sugar consists of about 49 locomotives performing runs for 3 mills. So we analyzed travel and shunt activity information. So to do that, we ran our algorithm and put the results in a table grouped by run activities for each mill. And then we put all this table in pies for each mill. So based on these pies, we draw some observations. So the first one is that locomotives spend most of the time traveling, which makes sense. And we also observed that shunting times are different for each mill. And we also observed that, especially at race course, locomotives perform a lot of shunting activities, a lot of junction activities. So we then combine these pies into one big pie for the 3 mills. And then we analyze shunting times. And then we observed that on average, locomotives take 50 minutes to shunt. And we also noticed that about 25% of those shunts, locomotives took 11 minutes or less. So then, for example, Farley Mill, which has 44 runs a day. If we were able to reduce average shunt time from 15 to 11 minutes, we could potentially save 12 hours a day, which is the same as 1 shift per day. So 1 shift per day equates to $100,000 per season. And then if we think about this figure across all 18 mills, we could potentially save $1.8 million. Although mills would still have to invest some money in infrastructure. So we then decided to analyze shunt activities a bit closer. So we selected 9 sidings, which had a large number of deliveries and collections, and had different layouts and lengths. So we noticed that we observed that the average shunt time for bin deliveries were about 30 minutes, and for bin collection, 60 minutes. We then looked for trends between number of bins and shunting time. And then we observed that on average, shunting time increases about 1 minute for every additional 14 bins delivered, and increases 1 minute for every additional 7 bins collected. So we also observed that on average, shunting time may vary 3 minutes for delivery and 5 minutes for collections. So based on this analysis, we can conclude that average run activity duration can be determined. And also shunting times can affect travel time for runs that perform a large number of shunts. So as a future work in this algorithm, we want to add new reports or maybe change existing reports based on user feedback. And as I mentioned before, we were able to match about 50% of the runs between the GPS and Tilt Tools data. And we want to increase this number. And to do that, we want to add a routine in Tilt Tools, which process real-time GPS data to indicate to traffic officers when runs are commenced or finished. So this routine has been implemented already, but we still need to test it during the crushing season. So we are looking for volunteers if anyone is interested. So the last one is we want to detect runs that start and end at sidings or in some parts of the network outside the mill yard. And to do that, we might have to define sidings as regions, similar to mill yards. So the second algorithm that we developed in this report is the arrival time algorithm. And the rationale behind is that locomotive arrival time information allows traffic officers to better anticipate run activities. So with this information, traffic officers can pass by this information to harvesters and mill staff, and they can plan their working time better. So for example, if a harvester knows that for some reason locomotives are running late, he can organize earlier cribby breaks or maintenance. And similarly, if mill staff know that locomotives are running late, he can better prepare themselves and change the mill rate, so slow down in some cases. So again, to develop this algorithm, we use some of the ACTS routines. So as I mentioned before, ACTS simulates ledgers, or simulates schedules in Tilt Tools. And one of the outcomes is that it generates siding arrival times. So we then use this routine so that we can simulate the actual schedule to determine current siding arrival times. So in other words, we know what the locomotive is going to do at real time. So after that, we process real-time GPS data so that we can determine where locomotives are and also what activities locomotives have performed so that we know what activities locomotives will perform next. And also depending on the complexity of the schedule, the arrival time algorithm may slow down other processes in Tilt Tools. So we added a feature where users can set up one PC exclusively to run the arrival time algorithm. So this PC would run and then process data for the PCs. And to see what the arrival time looks like, the arrival time data looks like, so in Tilt Tools, you simply need to right-click a local run and then select down the bottom arrival times. So once you click that, a form similar like this would show up, which shows what activities the local will perform and what time. So to check how good the prediction is, we implemented a routine that simulates real-time GPS data based on historical data. And then this routine every hour would run the arrival time algorithm and then compare predicted siding arrival time against the actual arrival time. So we ran this routine with two Makai Sugar locomotives. setters and folding within this period. And our first observation was that we were able to predict about 80% of the deliveries defining till tools, entering till tools. So we then put the results in a box plot report. So we noticed that, so this is the 8-hour marks behind the actual siding arrival time. So we noticed that it was hard to predict the arrival time way before the actual siding arrival time. But we can also see that as we get closer to the actual siding arrival time, the algorithm gets more and more accurate. So we can also see that this is the 0 mark. We can also see that arrival time was predicted in general earlier. So that's why all the data is behind. It's below the 0 mark. So this is what our observation looks like. So arrival time prediction. So the arrival time was predicted within 96 minutes, 3 hours before, 60 minutes, 2 hours before, and 11 minutes, 1 hour before. And also arrival time was generally predicted earlier. So as a conclusion, arrival times are predicted earlier, and the reason is because ACT simulates ledgers with no delays in locomotive operations. And apart from that, ACT relies on the default locomotive speed and shunting times, which is entered in till tools. So which means that the algorithm will deliver better results with greater accuracy of locomotive and siding data in till tools. So as a future work in this algorithm, we want to be able to simulate future run activities by using other systems. So at the moment we just use ACT. So we might interface this algorithm with the real-time scheduling system, for example. And we also want to use the results from the historical GPS data algorithm, since it processes average shunt time and locomotive speed, segment average speed, for example. So just to finalize the presentation, so just an overview of this research. So ACT was essential for us, and also runs are matched between till tools and GPS data based on run start time and mil. And also the accuracy will increase if run start times are entered accurately. Mil yard, railway, and sidings are accurate in Mapinfo, and also local speed and shunting time information entered accurately in till tools. So I just would like to acknowledge all the parties that supported us and funded us throughout these 2 years. So thank you all for listening. I'm happy to answer all your questions now.